So now let's move over to the sine function, okay, and the parent function for sine. To fully understand how the sine function came to be, we have to first test a few values of theta, thereafter plot the graph, right? So what I'm going to do is we're going to work with the function y is equal to sine of theta, but we're going to input values and find out, examine what outputs we get. We're then going to plot those inputs to those outputs and then join the curve and see what we get, right? What function we have. We will intentionally restrict the domain of the function so that it exists from 0 degrees to 360 degrees, right? Remember I said when we worked with the parabolic function, I said you can't only input positive values. You have to input both positive and negative values, right? And I said the reason we do that is because I understood something about the parabolic function. I knew that there's basically two halves to it. Now here I'm also telling you something else. I'm telling you a fact that we will restrict the domain between 0 and 360 degrees. Why we do that is something that you will learn as we progress through the course. But for now, I'm just going to say that we're going to restrict it from 0 to 360. Right? But if you read ahead, you would see here that this is due to the periodicity of the sine, cos, and tan function. What that means is that the function will continuously repeat itself in that same pattern. And so if I go and input a value bigger than 360, there's no point of doing it. Right? Because the function is just going to become periodic. It's just going to be the same thing over and over. So we don't want to know what the general pattern is. I just want to examine the most basic form of it, which is found in 0 and 360 degrees. Anything bigger than that is just unnecessary information. It's just noise. Let's understand it for this interval. And because we know that it'll repeat itself over and over, then we can understand it for however many intervals will be given. Okay. In other words, these functions will recur or repeat itself over and over in these intervals. Same story. Remember, every graph we draw is the parent function. Thereafter, we will shift and stretch the function with other variables or constants. Okay, so let's draw this function. So for theta, we'll have 0, 30, 60, 90, 120, 150, 180, 210, and so on. All right, let's input these values into our calculator. These are the outputs that we get. 0, half, 0,87, 1, 0,87, half, 0. You see, the fact that these values are repeating tells us a lot, right? It tells us something's happening. We're reaching a turning point, a maximum, then it's decreasing, behaving very similar to the parabolic function. And then we can see we're going into the negative side, right? And we get these values. When you plot these values and you join the curve, this is what we get. It looks like this. It goes up, down, up, right? Up, down, up. Now, this is extremely important. This visual should be ingrained in your memory. When I talk about the sine function, what does the y equal to sine theta function looks like? It looks like this here. Up, down, up. Right? The next thing that I want you to remember are these very critical points. What points? 0, 90, 180, 360, and 270. Right? Because these are what we call the x-intercepts. Right? The y-intercept is also here. The turning points are important, and so on. So those are what we call the critical points. They're very important. We have to remember them. Because the reason I say we have to remember this, right? The reason I say we have to remember this is because let's say that I want to find out the x-intercepts of this function. So I'm just going to do something quickly, right? The x-intercept is what? The point where y is equal to 0. So if I say sine of theta is equal to 0 and I put theta is equal to the inverse of sine into the calculator of 0, what do I get? I'll get 0. Put this into the calculator, you get 0. Shift sine of 0. What answer do we get? 0. But is that actually correct? It is partially correct. Because the x-intercepts is what? It's 0, 180, and 360 degrees. Because the function passes through the x-axis at these 3 points. And so not knowing this, listen to what I'm saying. Not knowing this, you will lose marks for it. This is why understanding the parent function in depth and committing this shape of the function in your mind is so important. Because if you don't do that, you will not see this. Just putting your answers into the calculator will give you a very visual view. And this is why visuals are so important. Exactly like we did with the parabolic function. When you solve for the x-intercepts, if you do it incorrectly, you'll only get one answer. But we know that more often than not, we have 2 x-intercepts, right? Why? Is because the visual tells us that. The visual says it to us. But if you don't do it in the correct way, you won't get 2 x-intercepts. You'll only get 1. Right? So this is why it's so important that you commit this visual to mind. Right? So we know that there's 3 x-intercepts, there's 1 y-intercept, and the 2 turning points at 90 and 270. right? So you need to remember these values, right? But we'll get to it. Don't worry, we'll get to it and I'll categorize all of this information for you. Note, I want you to commit the shape to memory and the important points of this function, like the intercepts and the turning points. I've explained this. Your understanding of this parent function will heavily impact how well you understand this topic. Very bold statement, right? As I said, to me, mathematics is understood fully with functions because it helps you visualize what these numbers mean. But not any numbers, more specifically under the realm of trigonometry. So trigonometric function helps you understand trigonometry, right? The linear, parabolic, hyperbolic, and exponential functions help you understand algebra, right? And we can bring in the cubic and the quartic function at higher grades. Okay, so that's just the sine function. Let's understand the components of the sine function, exactly as we did with the parabola, the hyperbola, the exponential function, and the linear function. We do the exact same thing here. We talk about the domain and range, intercepts, and turning points. So these are the things that we must remember. Remember, again, we will not give these things names if they were not significant. We could have just called it some random point on the graph. The fact that I'm bringing this to your attention means you need to remember it. Okay, the domain of any function is the x values for which the function exists. But we don't say x here, now we say the theta values for which the function exists. Since we restrict the domain, or we have a restriction on the theta values, right, or the x values, we say that the sine function exists between 0 and 360 degrees. So looking at this function, what is the domain of this specific function? It is between 0 and 360 degrees. Why we did that is because we know the function is going to repeat. It's just going to continuously do that. It's just going to continuously do that. But we're not worried about what it does over and over. We just want to know, okay, one segment, one complete segment. If you have to give me the complete image in the most basic form, what would that look like? It would look like this. Then everything else will just be a re-expression of this here. But it's just going to keep repeating. So if it's going to repeat, let's understand it in the most basic and complete form before we worry about what it does repeatedly. Okay. So that's why we say that the domain is between 0 and 360 degrees. Now remember, this can go on forever. It could be between 0 and 3600, let's say, right? But we're not worried about that. We're saying we intentionally restricting the domain between this interval. Understood, right? It can be whatever, but we intentionally restricting it because we know that the function repeats itself. Okay. The range of any function is the y values for which the function exists. In the sine function, we can see that the graph will always output values that lie between 1 and 0. So that's another observation that we can make. After plotting this point between this interval here, we can see that the function peaks at 1. Right? If you go slightly to the left, you'll get a number that's lower than 1. Slightly to the right, you get a number that's lower than 1. Here as well. If you go slightly to the left, you get a number that's slightly bigger than -1. And if you go slightly to the right, you get a number that's slightly bigger than -1. So this is why this is the max and this is the minimum. And so when you have a max and a minimum, then we have a turning point. Okay? The range of the function, the extreme, the highest and the lowest value will be between 1 and -1. Okay? Intercepts. The x-intercept is a point in which the graph intersects the x-axis, or the horizontal axis, or the theta axis, where y is equal to 0. However, I want you to remember an additional point. The x-intercept is also the point at which the nature of the y values change. Right? But we're not worried about that for now. But if you want to think of it, I've already discussed this. See, at the x-intercept, what happens? Y is equal to 0. If I move slightly to the left, what happens? Y is positive. Slightly to the right, y is negative. Right? So this was very important for interpretation type questions. Right? This is very important because if they ask you for what values of theta, you sine of theta less than 0. They're asking you for what values of theta is y less than 0. Because we're analyzing the nature of the y values, you go to what? The x-intercept. I've talked about this under the interpretation type questions. And so if we know that, I'll go to my x-intercepts and say, okay, where is that occurring? Oh, right. So these are the x-intercepts. So let's go there. If I go between these two x-intercepts, y is positive. So I'm not worried about that. But if I look between these two x-intercepts, everything below is what? Y is negative. So therefore I take this segment. Right? Because we're basically saying there's infinitely many points that I can look at. But because we want to know something about the nature of the y values, what helps us solve such a question? It's the x-intercepts. Because at the x-intercepts, the nature of the y value changes. Right? So we remember the process of elimination. From many things, we're trying to zoom down and say, okay, what's that one factor, that variable that will affect the nature of the y value? It's only the x-intercept that can affect it. Okay? So that's the reason why we take it to be that. So yeah, that's that. but don't worry about that for now. To solve for this x value, we let y equal to 0. But I've already told you, if you do that, you'll only get one solution. So this is why you need to commit these to memory, right? So the x-intercepts is 0 degrees, 180 degrees, and 360 degrees, okay? The y-intercept is the point at which the graph intersects the y-axis, right? To solve for this, we let x equal to 0. Here, because there's only one y-intercept, you can put it into the calculator and you can get it. But it's important that you commit this to memory and you know that it's at 0. The turning point or the stationary point is a point where the function's y value reaches a maximum or a minimum. This is equivalent to the range of the function, since it's the maximum or minimum for which the function exists. Right? Where do we get these values? It's 90 and 270. Right? So it's 90 and 270. So if you go here, at 90 degrees, the function is 1, and at 270, the function is minus 1. And so what I'm saying is, if I was in the paper, this is what I would do. As soon as I'm given a question and I know it's a paper 2, this is what I would do. I would first go sketch my sine function like this, nice and neatly, right? I would say, okay, this is 1. It peaks at 90 degrees. I know that this is minus 1. It has a trough at, what's this value? 270 degrees. Then I look at my x-intercepts. I know that that will be 0. I know that this will be 180 degrees and this will be 360 degrees, right? Alternatively, what you can do is, you can do this. You can, let's learn the x-intercepts, right? Let's learn the x-intercepts. So the x-intercepts are at 180 degrees and 360 degrees. The peak will be between 0 and 180 degrees, which is 90. So I'll say 180 degrees plus 0 divided by 2. It's exactly halfway here. And here I'll say 360 degrees, right? Plus 180 degrees divided by 2 will give you this value of 270 degrees. But these are your extremely important points that you need to remember. Y-intercept, x-intercepts, turning points. Can you see that? Have to remember it. And range between 1 and minus 1. Trust me, this is going to open us to very powerful calculations. But you have to understand this. You have to. The period of a trigonometric function is the length for one complete cycle. So what's the length, or how much do I need to go in order for me to have the complete image of the sine function? It's 360 degrees. So I need to go from here, from 0 to 360 degrees is the complete image of the sine function. Exactly as I said with the parabola. If you only do positive values, you have an incomplete view. So therefore, you have to do the negative values as well. Right? How do we know this? Is because when you sketch it, you see it by observation. It's this. So now we have to be very cautious when we're working with it. Right? Again, see here, it is the length along the x-axis of one complete cycle of the function. So the period of the sine function is what? 360 degrees. So every 360 degrees. So let's say I was here to here. Every 360 degrees, that's one complete function. Okay, every 360 degrees, you get one complete sine function. Right? And exactly as I said, yeah, after every 360 degrees, the sine function will repeat itself. Right? And I want you to write this here. This is why I said that for certain questions, there could be infinitely many solutions. Okay? When we said sine of theta equals to 0,5, right? You put this into the calculator, you got an answer of 30 degrees. Okay? But if you look at this, yes, here. Half is somewhere here, 0,5. If I come down here, this is 30 degrees. But see here, there's another solution here. This could be another solution, right? And then if the function completes itself again, right? If the function completes itself again, these values here will also spit out the value of half. Can you see that? So this is why we're saying that there could be infinitely many solutions, right? And when we solve these problems, this is why they said in those problems, they said, okay, theta must be between 0 degrees and 90 degrees. They told you it must be between or in quadrant 1. Right? But if you don't understand that, I'm going to get to these problems and you're going to see the power of this. You're going to see the power of this. So all you got to remember now is, if you didn't remember anything, all you got to remember is you have to commit these values to memory. 0, 90, 180, 270, and 360. You need to remember your domain is set by us because we're restricting it. We need to know that the range of the standard, the parent function, no shifts, no translations, is between -1 and 1. The intercept is 0, 180, 360. Your y-intercept is 0 degrees. Your turning point is 90 and 270. And the period, after every 360 degrees, the function will repeat itself. It'll do the same thing over and over. Right? So we're just saying that the period is 360 degrees. What does that mean? After every 360 degrees, the function will repeat itself. It'll do the same thing again. Okay, so yeah, so that's basically everything that you need to know for the parent function of sine. Now we'll affect the parent function and we will shift and translate it, right? Or we'll transform and translate it to get the sine function in a more generalized form. Why do we do this? It's because it enables us to expand our applications with sine. Right? You'll never always be given sine of theta. You'll be given things like y is equal to 2 sine of theta. How do you deal with a problem like this? Or y is equal to 2 sine of theta plus 1. Right? Can you see? So now we can expand our applications with sine and cos and tan once we transform and translate it. Okay. Right. So now we can move over to the generalized form of sine. Like all functions, the sine function can be expressed in a more generalized form. In the generalized form, we can shift and stretch the function by increasing or decreasing the values of the constants. Which constants? These constants here, a and q. Let's first express the generalized form of the function, thereafter examine the effects of these constants. So this is the most generalized form, right? Where we say y is equal to a sine theta plus q. Exactly like how we had for y is equal to x squared is the parent function, but the parabolic function in a more generalized form is what? Y is equal to ax squared plus q. It's the exact same idea here, right? It was important that we examine the y is equal to sine theta function as it is the parent function for sine. Exactly as I said, if ever we want to translate, mean move up and down or left and right, or transform, meaning stretch the function, we will need to examine the parent function first. Everything is relative to some standard, and in this sense, the standard is the parent function. Right, so now let's examine the effect of a and q on the parent function y is equal to sine theta. The effect of q shifts the function vertically, either up or down. So if you ignore the constant a, let's work with one thing at a time. We have two things, but let's work with one thing at a time. So if I had the function y is equal to sine of theta, when I input 0 degrees, if I input 90 degrees, 180 degrees, 270 degrees, and 360 degrees, what's the outputs? Right? What's the output? For 0 degrees, we get 0. We get 0, 1, 0, minus 1, 0. Okay? Remember, let's go back to the sketch, quick sketch. There's it here. 0, 180, 360. In between 180 and 360 is 270. In between 180 and 0 is 90. Right? So that's how we get 1 and minus 1 here. But now if we do this, listen to this. If we do this, y is equal to sine theta plus 1. What we're essentially doing is, we first input theta, isn't it? Once we input theta, we get these corresponding, what? Outputs. And so to all of these outputs, what are we going to do now? We're going to add 1. And so before, at 0 degrees, we had 0. But now, because we add 1 to that output, we'll get 1. Right? Watch here. Before, at 90 degrees, we had 1. Now, because we're adding 1 to it, we get 2. At 180 degrees, we'll get 1. At 270 degrees, if you add 1 to minus 1, you get 0. At 360 degrees, if you add 1 to 0, you get 1. And so when you sketch this function now what will happen is at 0, it'll be 1. At 90, it'll be 2, somewhere there. At 180, it is 1. So 180 is approximately here. 360, it's 1. At 270 degrees, which is in between here, it is what? 0. So right here. And so what's going to happen is the function's going to do this. So before, can you see it was it was oscillating around the x-axis. Now it's oscillating around this line here. Y is equal to 1. Y equal to 1. It's oscillating along that line. So that's not like an asymptote or anything. We just say it's oscillating along that point. But effectively what you can see is we shifted the function up. We took this entire function, we added 1 to all of the infinitely many points, and it moved it up by 1. Right? Right, so the green function is the parent function. Now when I add a q value to the parent function, let's look at the black function. When you add a value, can you see what it does? It shifts the function up. Right? When you put in negative values or subtractive values, see what happens is the function shifts down. So we take all of the outputs of the parent function and we subtract by 1. Now we're taking all of the outputs of the parent function and we're subtracting by 3. And you do that for all of the infinitely many points and we get the new function, the translated function. Okay? But if it's a positive, then obviously it shifts the function up. So here it's 0. They overlap. Once you start adding by increments or values, and it shifts the function up. Okay, so that's the effect of Q. Very simple stuff. Very, very simple stuff. Let's take this out. Right. Now let's look at the effect of A. A affects the amplitude of the graph. Now, that's a new word that we learned. The amplitude is basically this distance here, right? It's the displacement from what we call the equilibrium. So see this part here? This is what we call the equilibrium. It's the displacement from the equilibrium to the maximum, or the displacement from the equilibrium to the minimum, right? That's called the equilibrium. So when we had that value y equal to 1 in the previous scenario, that became the equilibrium, okay? Because it oscillates about the equilibrium. So basically what we say, it affects the amplitude. So what's going to happen now is this function is going to do what? It's going to start to stretch like that there. Can you see that? It's going to start to stretch. So this is what we do transformations now. Here we did translations. Now we're going to do transformation where we stretch and compress the graph vertically. And so if we ignore Q, we have two things. Let's work with one at a time. So keep the Q constant. And we look at A relative to the parent function, then this is what happens. If it is bigger than 1, the amplitude increases. Think about it like this here. We had y is equal to sine of theta. When you put in 0, what did you get? 0. When you put in 90 degrees, what did you get? 1. But now if I have y is equal to 2 sine of theta, before we had, so this will remain the same, right? Before we had at 90 degrees, we had 1, but now at 90 degrees, what we will have? 2. It stretched it, right? So it stretches the function. But if it's a fraction value, like half, before it'll be 1, but if you multiply 1 by half, what do you get? Half. So it compresses the function. It makes it fatter. When we're stretching it, we're making it thinner and longer. Okay? If A is negative, then the function shifts about the x-axis. And so what happens if we shift about the x-axis? Then all of these points, watch here. So look at this. Let's look at this part here, right? Let's look at this here. All of these points here, when you reflect something about the x-axis, all of the points reflect perpendicular to the x-axis and by the same distance away. And so all of these points here will go here. This point will go down somewhere here. This point will stay here because it's neither above or below the axis. It's on the x-axis. And if you do that for the infinitely many points, we get this new function that looks like this here. So that's what happens when A is negative, right? It flips the function. So instead of going up, down, up, now we're going down, up, down. Can you see that? That's what happens when you have a negative A value. And then again, same story. If you have a value that is less than -1, so it's going in the negative direction, like -2. The minus means that it'll reflect about the x-axis, and then 2 means it'll stretch the function, isn't it? If I had something like -half, the minus means that it's reflected about the x-axis. The half means that it'll contract or compress the function. Right, so that's all the minus does. So if we do it here, the green function is what? The parent function. Now if you apply this value to it, and you put a value that is bigger than 1, can you see what happens? It stretches the function. It's making it thinner. It's making it thinner. But if you have values that are smaller, like fraction values, can you see what it's doing? It's compressing it. Remember, the green function is the parent function. Can you see it compresses it? It gets thinner. Right? And if it's 0, obviously it becomes a straight line. And then if you go in the negative direction, can you see that? Once you go in the negative direction, same idea applies, right? But it's just happening in the negative side, right? You can see it gets thinner, but in the negative side, right? Or it gets fatter in the negative side. So if I made this here negative, right? If we made this here and call this the parent function in the negative direction, if you had something like -half, can you see that? The negative parent function, relative to the negative parent function, it's compressed. Right? If you go bigger values than -1 relative to the negative parent function, we are stretching the function. But all the negative does is it reflects it about the x-axis. So very simple stuff. That's what A and Q does. And then the amplitude of the function is the measure of its maximum displacement or magnitude from its equilibrium. So what is the distance from here to here? Right? If you want to know how you get that, it's basically your maximum value minus your minimum value divided by 2. Max minus minimum divided by 2. And it'll always be a positive value because we're saying it's the magnitude, right? It's the distance from here to there. Okay? So yes, very simple stuff. Very, very simple stuff. Then we can move over to the components of the generalized sine function. The domain of any function is the x values for which the function exists. Since we restrict the theta values that we can use, it'll be between 0 and 360. I already said that. Right? We're working intentionally. We said because it repeats after 360, we're just going to work in this interval here. Right? The range of any function is the y values for which the function exists. Since the constants a and q will both have an effect on the range, right, of the sine function, we can use the formula as follows. And we can start off with this fact. We know that sine of theta lies between -1 and 1. That's what we know, right? If the function has an amplitude of a, right, so if I multiply this here by a, then I have to multiply both these sides here by a. So we're not changing it, we're re-expressing it. So we can come down to a very important conclusion. So if I add a, then I will have to multiply by a. So let me show you this visually. This is the normal function, right? If I multiply by a now, it's going to do this, isn't it? So now the range will no longer be between 1 and -1. Now it will be between what? Think about it. Between a and -a. Can you see that? So this is what we're doing. We're re-expressing it. Okay? But then what happens if I shift the function up and down? So if I took this purple function and I moved it up, then what's going to happen? Let's say I moved it 1 unit up. It's going to do this here. So now the range will be between here, whatever that is, and here. And so what we do is, if we have to express this mathematically, if I add q to this, then I need to add q to that and that. So we're not changing it. We're starting off from a logical fact and we are re-expressing it. And so every point on this function will increase by q, isn't it? Or decrease by q. And so if you do that, now we can see that the function lies between this and this, whatever that value is. And so when you're given this, you can use this formula here, or you can just sketch the function quickly and see what you output. But what we're saying is, starting from this fact, if you have an amplitude and if you have a vertical shift, then this is what the values will look like. So it'll be this amplitude plus, let's say, whatever the q value is. So let's say the amplitude here is -a. Let's say that this minimum value here is -3, right? It's -a, so it has to be -3. And if we shift this function 1 unit up, now the minimum value won't be -3, what it'll be? -2, which is the same as saying -a plus the q value. Then we look at this here. Let's look at this maximum. This maximum value is a, or let's say 3. But if we shift it up, then it'll be 3 plus 1, right? So it'll be, or a plus 1. And that's how we get it, yeah, in a more generalized form. So these are just generalized values. But the nature of the output can be any real value. And it can be fractional values, it can be whatever. So this is why we say f of theta has to be an element of real. So the outputs, the nature can be of any real value, so long as it's in between this minimum and that maximum. And you include both the extremes. Okay. Then we talk about the intercepts. Here as well, I've talked about this extensively. You find it by setting the x equal to 0 to find the y-intercept and y equal to 0 to find the x-intercept. But again, I must state this again. You won't be given complicated questions, but you must sketch the function. You have to sketch the function in order to see what you're doing. Because we know that, see, sometimes there could be no x-intercepts, like that there. Right? It's oscillating about this line y is equal to 2. Sometimes it could just be 1, where it does something like this here. Y equal to 1. Can you see that it'll do this here? There's one x-intercept. Can you see that? So you have to sketch the function to see what you're given. Or sometimes it could be given 3. Right? You could be given 3. Exactly as it comes in the normal function. 1, 2, 3. Right? So you have to sketch the function and try to sketch it and draw it to scale so you can see exactly what you're doing. And always start off with what? The parent function. So first you'll do this. I'll draw the parent function, right? Then I'll affect the amplitude. And then I'll affect the shift, right? Or the q value. And so if I was given the function y is equal to half sine theta plus 1, then what I'll do is I'll first sketch my parent function. Parent function I know does this here. Right? So that's 0, 180, 360. And I'll sketch this lightly in pencil. Then I'll say, okay, the half will affect the amplitude, so this will come somewhere here. But remember, now normally it's at 1 and -1. Now it'll be here and here. So it'll do this here. But remember, the x-intercepts can't change because you say half times 0 is what? 0. And then I'll say, okay, let me add 1 to it. So I'll take all of these points here. Don't have to do it for all of it. Just do it for a few. I just do it for a few. So I'll do it for maybe these 5 points. and I'll just shift it up by 1 unit. So normally this point is at 0, now where it'll go? At 1. Normally this point is at half, where it'll go now? Go to 1.5. Normally this point is at 0, where will it go? It'll go here. Normally this point is at minus half, now where it'll go? If I add 1 to minus half, we get half. So it'll go right here. And you have to trace it. It gets very confusing. This is at 0, now it'll go at 1. And so what will happen is, it'll do this here. Right? Alternatively, the way you can view it is like this here. I have this value of 1, right? So it has to oscillate about this point here, y is equal to 1. And it has to oscillate about this line here, y is equal to 1. And so once I know it's going to oscillate about that line, so let me take out all of this noise, right? And it oscillates at about that point there. Then what I'll do is I'll do the following. I'll say, okay, I know that the amplitude is half. So from 1, this needs to move half unit up there and down half unit, right? And then you start sketching the point. But the safest thing to do, right? That's only once you experienced. The safest thing is to draw your parent function, affect the amplitude, and then do the shift. Safest thing to do. That's the safest thing to do when you're sketching it. But if you, as you get familiar with it, I know that this point here, the line, it has to oscillate at about that line. It has to oscillate about that line, y is equal to 1. And then the displacement is half and half. But yeah, that if you don't know how to do that, don't do it. Just stick to what I just said there. Okay. Then the turning point. How do you do the turning point? Again, go back to your parent function. There's nothing, it's not difficult. Go back to the parent function. The turning point, the parent function does this here. 0, 90, 270. Right? If I multiply by a, what's going to happen? If I multiply by a, what's going to happen? The function is going to stretch up, isn't it? Like that there. So therefore, now the turning point will be at a and minus a. But if I take that a value and now if I add by q units to it, right? So let's see. Here now it's a and minus a. So it'll be a and minus a. That's the turning point at 90 and 270. But if I add by q units, if I add 1 to this, now it won't be a and minus a. Now it'll be a plus whatever q units, plus q, and minus a plus q units. It'll go from minus a to somewhere here. I can see it because you're adding by q here. Can you see that? So this is why we say more generally, the turning point is at 90 degrees and a plus q units, and 270 degrees here and minus a plus q units. So it's still along these values, but it's just shifting up and stretching. Understood? All right, we didn't get to the complicated stuff yet where we deal with left and right shifts. That's going to be done at grade 11. But for now, this you can commit this formula to memory, or if, and what you should do is you should understand exactly what you do. Right? And how everything comes from that same logic. Start with the parent function, then affect the amplitude, then affect the shift. That's how we come to these conclusions. Okay. And then the period of the function, even if the sine function in a more generalized form will still be 360 degrees because the pattern will still repeat after. So I can take this function, I can stretch it up this way. Right, watch here. I can take this function, stretch it up this way like this here, but the function still repeats itself after 360 degrees. So it does not affect the period of the function. The a and the q value will not affect the period of the period of the function. So therefore we say it'll still be 360 degrees. Okay. So yeah, that's what you need to remember there. But we will learn a constant k, which is done at grade 11, where you will start affecting the period of the function. So I'm just preparing you for that there. But you just need to remember that it'll still be that standard 360 degrees. Whether you affect the amplitude or the vertical shift, it'll still remain the same.